Okay, so we were discussing this force on current carrying conductor placed in a magnetic field concept, and we discussed this yesterday that the main reason is the interaction of the fields, interaction of two fields. The two fields are going to interact with each other, and then the two fields will create a stronger region around the wire and a weaker region, and then the wire will be in the middle, and the stronger wire will push the wire towards the weaker region. That's how the force acts on the wire. So main thing is interaction of the two magnetic fields. So the thing is we can change the direction of the force by changing the direction of current in the wire or by swiping the magnetic poles, and we can increase or decrease the amount of force by decreasing or increasing the current, or by decreasing or increasing the magnetic field strength. And we know that the magnetic force acting on the wire is proportional to magnetic field strength. Like how stronger the magnets are, then that force is also proportional to flow of current in the wire, and that force is proportional to length of the wire inside the magnetic field. And the most important factor is the angle between them. So combining all these factors, we get force equals BIL sine theta. So this is the expression that we can use to find the magnetic force acting on current carrying wire placed inside a magnetic field. Now for the relations, and we plot the graph between force and magnetic field strength, force and current, force and length, and force and sine theta. So as all of the relations are directly related, that's why these are directly proportional to each other. Now for the like the sine theta and force are directly proportional to each other, but if we plot a graph between force and the angle, then that graph is not a straight line but a decreasing gradient curve. We know that if theta is 0, sine theta would be 0. For 30-degree, sine theta is 0.5. For 60, it is 0.866, and for 90, it is 1. So if we take the sine value, then we can get the corresponding force value as well. For example, we know that maximum force is BIL sine 90. Like maximum force happen when angle is 90, because sine 90 equals 1. So when sine 90 equals 1, then this is F is BIL. This is the maximum force. So that's why at 90 your force is maximum, which is 1. So that is your first point. After that, you can replace the values. Like for sine 30, you know, it is sine for angle 30, sine theta is 0.5. So it means that at 30-degree your force will be half of the maximum. So half of the maximum is at 30. And then similarly you put 60 in sine 60, so that is 0.866. So it means force at 60-degree is 0.866 of your maximum force. So that's how you plot the 60-degree over there, which is like roughly 0.866. You got these points, and then you connect them with the help of this line. So that's how you plot the graph between force and angle, and this is important graph. This often comes in the exam as well. Okay, so now let's just vary the angle of the wire in the magnetic field. Okay, you can look here. This is the first diagram in which the wire is parallel to the magnetic field. You can see that the magnetic field lines are from north to south, and current is also in the parallel. So it means that the angle is 0. So if the angle is 0, of course the force is 0. So it means here the force is 0 at angle 0. Okay, then what you have done is you have tilted that wire to 90-degree angle. Now you can see that clearly the current is perpendicular to the magnetic field. So over here the force is maximum, so this is where your force is maximum. Then again you tilt it to 90 degree, like 180 degree from the initial position, and now you can see that both current and magnetic field are parallel again, so this again causes force to be 0 over here. So force is 0. And when again you tilted it further 90, like 270 from the start, it's again perpendicular to the magnetic field. Current is perpendicular to magnetic field, so again a maximum force occurs. But this time the direction of force will change because you have changed the direction of the current. So then your force is maximum but in negative direction. So that's how we can plot uh, we can plot the graph, which is in the form of a sine wave between force and theta if you are rotating a wire from 0 to 360 degree inside a uniform magnetic field. Okay, let's move forward to the next concept in it, and that concept is very important: how you can find the direction of the magnetic force. So in order to get the direction of the magnetic force, we use the most famous rule, which is Fleming's left hand rule. So in Fleming's left hand rule, of course, we use left hand, and then we use three things. One is the thumb, second is the first finger, and then the third one is the middle finger. So we use left hand, and then we use thumb, first finger, and middle finger, such that the three are in at right angle to each other, right? So uh, the thumb represents the direction of the force that the wire is going to experience. B is the magnetic field strength or magnetic flux density, which you will point by the first finger, like you will point your first finger of the left hand towards the direction of magnetic field. And then the second finger you will point towards the direction of current, which is like flow of positive charges. Okay, so all these are mutually perpendicular to each other. So as it is given in the diagram, you can see that the north to south, just try to practice this with your left hand. Um, okay, hold on for a while. Okay, so I was telling you that what you have to do is you have to apply the rule on the screen as it is indicated over here to the right side. Point your left hand in front of the screen and then point the first finger. Don't bend the first finger, just open your hand, whole fingers open, and then point your first finger towards your right, because north to south magnetic field is right. And then you have to close your last two fingers, just close them towards your palm, and then point middle finger towards you. Point middle finger towards you, because you can see in the diagram that current is seems to be coming out of the screen, or it is slightly towards your right. And then the thumb is pointing upward, so it means that this wire is going to experience the force in upward direction. Okay, so over here, an important, this is known as like Fleming's left hand rule, and its main implementation is you have to you can use it to find direction of magnetic force on a current carrying wire. Okay, the next thing now is the magnetic flux density. We know that from this expression, F is BIL sine theta. You can make B as the subject, so it is F over IL sine theta. And furthermore, if we say that sine theta is 90, so we can write it as B is F over IL. So this is the main equation that we can use to define magnetic field strength. Okay, so let's define it. Magnetic field strength. Um, it is clear that magnetic flux density is equal to force experienced per unit length of a conductor carrying per unit current when placed perpendicular to the magnetic field lines. So like you can use this equation to define magnetic flux density or magnetic field strength. So it is again, it is magnetic flux density equal to magnetic force experienced per unit length of conductor carrying unit current and held perpendicular to the magnetic field. And it is a vector quantity, and its direction is towards the deflection of the north pole, or it means that its direction is towards the direction of the force. Like the direction of B is always towards the direction of the force on the moving charge. So or moving charge or the moving wire. um, its unit is Tesla, which is denoted by capital T. So this is very important exam definition as well. You have to define Tesla. So whenever you have to define any unit, you write its formula. So B is F over IL sine theta. And then you put the unit. For B, the unit is Tesla. For F, the unit is Newton. For I, it is ampere. For length, it is meter. You can avoid this sine 90 over here. No need to write every time sine 90 over there. So like you can avoid that as well. No need to write this. Okay. Okay, now we can define this as magnetic flux density is 1 Tesla if a force of 1 Newton is experienced by 1 meter length of a conductor carrying 1 ampere current when placed perpendicular to the magnetic field. So again, the thing is you have to use this equation to define the Tesla. Like this equation is used to define magnetic field strength, and the same equation is used to define the unit of magnetic field strength, which is Tesla. So what is magnetic field strength? It is magnetic force acting per unit length of the wire carrying unit current and held perpendicular to the magnetic field. And how we define Tesla? Just put the units in this equation and then we say, okay, just translate this like 1 Tesla is equal to 1 Newton per ampere per meter. So in words, it makes 1 Tesla is the amount of magnetic flux density when 1 Newton of force is acted on a wire of length 1 meter carrying 1 ampere current and held perpendicular to the magnetic field. Okay, the next topic is quite interesting. It is the further extension of force between two conductors carrying current, because whenever two conductors are there having current, so they act like magnets. So their magnetic field will interfere with each other. So two parallel current carrying wires are actually acting like two magnets. So we know that as two magnets, if you bring two different magnets closer together, so what they're going to do is either they are going to attract each other or repel. Like if this is north south, south north, and this is like south north, and this is south south. So you can clearly see here that in this diagram they're going to attract, and in the bottom diagram they are going to repel. So we conclude from here that if you bring opposite poles together, attraction happen, and if you bring similar pole together, repulsion happen. This is the case with the solid magnets. Now let's apply the same rule on the current carrying wires. So when two current carrying wires are placed closer to each other, then they behave like magnets. Why they behave like magnets? Because they have magnetic field around them, and the magnetic field of both the wires is going to interact with each other, and then the magnetic field will interact with each other. Of course, stronger and weaker regions of field will be generated, and this will cause a force to act on both the wires. So let's say in the case one, we have two wires in which current is flowing in the same direction. So just focus on this image. Okay, these are the two wires in which two currents IP and IQ, like P and Q are the wires in which current is flowing in downward direction. So as current is flowing in downward direction, so what you do is, first thing that you do is you just plot the direction of magnetic field around them. So using right hand rule, you have to use right hand rule. Why you use right hand rule? Because you have to find direction of magnetic field. To find magnetic field direction around wires. So this is the first thing that you are going to do. So over here, the green circle represents the magnetic field. So as you point your thumb downward, the curl indicates the anti-clockwise direction. So it means that the magnetic fields are anti-clockwise. Now this is the first thing. The second thing you need to do is you need to focus on the region between the wire. This is point 2. So observe region between wires. So if you observe the region between the wire, you have to see that whether both the lines, magnetic field lines, have same direction or opposite. So it is clearly visible from here. Like you just ignore this at the moment. Just focus on one thing, that the direction of the magnetic field over here, it is opposite. So if the direction is opposite, they are going to repel each other. Like opposite lines are going to repel each other. So when opposite lines repel each other, the field over there is weak. So this is the weaker field, and automatically on the side, the strong field is going to be generated. So strong field will be on the sides and weak field is in the middle. Why field is weak in the middle? Because the two lines which are closer together, the lines are going in opposite direction. So obviously the lines are going to repel each other. I am talking about this region here, which I am highlighting. As here the magnetic fields are in opposite direction, so they repel, they go away from each other. The lines go away from each other. This generates a weaker field. And there is a very interesting example for this to understand. Let's say here is a thing, and let's say on this side a very strong person is sitting, and on this side a very weak person is sitting, and they have a competition. What they have the competition, they have to push this object. So of course the stronger person will push the object towards weaker person, right? So this will be the force. So same thing will be happening here. The stronger region which is around the wires are pushing the wires, because wire is the object for the magnetic field. So the stronger region is pushing the wire towards the weaker. So it means the end result is the strong region pushes the wire inward, the strong region pushes the wire inward. It means that an attractive force exists and both the wires started attracting each other. So let's apply this like here. This is the same description. This is the magnetic field. Like the magnetic field here is downward, here is upward. So it is written that attractive force exists as opposite magnetic poles are near each other. This is just another explanation, but I guess the good explanation is the one that I already gave you, that the two magnetic fields are going to be interacted with each other. That's why a force is acted upon them. So let's just have a quick review through this diagram. Again, in these wires, the current is flowing in the same direction, in upward direction. What you do is you plot the magnetic field, which over here is, of course, in anti-clockwise direction. Just ignore this for the moment. And you can see that over here, both the lines are again in opposite direction. So when they are in opposite direction, a weak field is there. So when on one side is weak, obviously on the other sides it will be stronger. So this stronger field is pushing the wire towards weaker field, and this stronger on the right is pushing the wire towards weaker. That's why an attractive force exists between the wires. So it means that we can conclude one thing from here, that if there are two parallel current carrying wires and the current is flowing in the same direction, then the wires are going to attract each other. And same is the case when both the wires or when the current is moving in the opposite direction. So when current is moving in opposite direction, like one is up and one is down, you just draw the magnetic field around them, and then you observe in the middle region.